Okay. All right, and next, group 3 is going to tell us about symbolic and ordinary powers of binomial edge ideals of threshold graphs.
Okay, first of all, thank you all for coming. We want to thank the RU organizers, the University of Nebraska Lincoln, and SEMA for this opportunity. Today we will be talking about joint work with LaClair and Pedro Ramírez. Okay, so first, what is a symbolic power? So if you take a prime ideal and m an integer greater or equal than 1, the m symbolic power is the ideal given by the elements in R, such that there exists some element Q not in P, such that the product RQ is in the nth ordinary power. Now, if I is a radical ideal with prime decomposition P1 up to PS, then the m symbolic power of I is the intersection of the m symbolic power of the primes in the prime decomposition. Now, we say that a cut set of a graph is it's a subset of the vertices with either no vertices or such that the connected components of the graph without the set T with one vertex is extremely lower than the connected components of G without the cut set. Now, each prime in the minimum prime decomposition of a binomial ideal is of this form. So you have a monomial ideal given by xi, yi for I and t, and the binomial ideals of the complete graphs given by the connected components. Now, turns out that the symbolic and ordinary powers do not always coincide. For the purposes of this project, we wonder when they do for binomial ideals. Now, previous work has been done, it's been proved by a bunch of families. This work has been done by Rinaldo Terai, Yahani, Bayati, and Ramati, Otani, Herzog, and Shamila Bayati. And it's important to notice that all of these families are net-free. Okay, so it's been conjectured by Rinaldo Terai that if G is a graph net-free, that is, it doesn't have this graph as in those subgraph, then the ordinary and symbolic powers coincide.
Now we know the problem we're dealing with. Let's talk about the tools we're using. Okay. Let's talk about the tools we're using. Recall that if you have a polynomial ring or a field K and you have an monomial ideal in there, this ideal will have a K basis. That K basis is all the monomials that are contained in the ideal. So something that we can do to prove a contention is that all the monomials contained in that ideal are in another ideal. That is, to show that the K basis is contained in another ideal. But we're not dealing with monomial ideals, we're dealing with binomial ideals. But there's a theory of standard monomials of determinantal ideals that uses or gives us the tools to use the same ideas. And as binomial ideals, its elements are 2 by 2 minors, and also it's a decomposition of primes. Recall that it's a monomial part and also a part with elements that are 2 by 2 minors. Without it could work. But what are standard monomials? Well, define the set pi with the all variables and add the fij's and equipped with this partial order. If they're in the same row or same column, they will be comparable. Also, if they are diagonal down, they will be comparable. Or if they're diagonal up, they will be comparable. And next, define an element is an arbitrary monomial if it's a product of the new variables. And is a standard monomial if it's a product of the new variables, which all of them are comparable. Just as in the normal case of a polynomial ring, with the new variables, the set of new variables generates a SECIHTI algebra of the ring, and the arbitrary monomials generates a SECIHTI vector space, the ring. But with this construction, we lost independency. So that's why we need the standard monomial thing. The set of all the standard monomial is a k-basis for the polynomial ring. But as this has happened, that not all arbitrary monomials are useful, but we need just standard monomials. Not even all binomial HDLs have a standard monomial basis. For a fact, take this example that we call the butterfly graph. The binomial HDL associated with this graph does not have a standard monomial k-basis, no matter what labeling do we put in this. Even know that the binomial HDL associated to this graph has just two associated primes. So not even in very simple examples we can assure it. The next question is, then when we have a standard monomial basis, and we found that it has a very close relation when we have any non-standard monomial when it's strained in it, then each one of the summands of the linear combination is in the ideal. So we have this definition. An ideal is strictly preserving if, for example, take a standard monomial, a non-standard. This can be written as a combination of standard monomials. We say that they are strictly preserving if this implies that each one of these are the ideal. And we prove that if for all t greater or equal than 1 and every p in the associated primes, if all p to the t is strictly preserved, then the binomial HDL to the power of the symbolic power t has a standard monomial k-basis. Standard monomial basis.
Okay, so now we have this property, which we really like, which says, okay, when we have straightening preserved, it gives us a standard monomial basis. The question is, when are we going to have the straightening preserved property for all of our prime ideals and all powers of them of every prime ideal in our associated primes? And so we proved that the following things are equivalent. One, which is the condition we want of straightening preserved. And second is this equation about the actual structure of each of these prime ideals. So let's understand this. If you remember from what Megan was talking about, each of these prime ideals, via the cut sets, you get some monomial part, which would be this, and you get a bunch of different complete sets, complete binomial ideals. And we're saying this works, we have the straightening preserved property if and only if you only get one complete part with greater than one vertex, and it's of this form. We have like, it's on the integers from 1 to a plus some other integer you tack on there, b. In fact, we can show this is actually equivalent. We don't actually need to tack on this extra thing, b. We can just say this is equivalent to existing sum labeling on G from like 1 up to n, where then every prime ideal has just monomial part and optionally at most one complete part, and that complete part is on vertices from 1 up to m. Now, of course, all the graphs which satisfy 2 are not going to just satisfy 3 for the same labeling, but the point of this theorem is that if you have some labeling for which 2 exists, you have some other labeling in which we also have condition 3. And importantly then, we can now prove that this is also equivalent to a condition which has nothing to do with the labeling. I mean, you don't want to just take your graph and try every single label and look at every possibility of the prime ideals and see if any of them work. And so this gives us a condition which is also equivalent to all the other 3 here, that our graph has this straightening preserved property for all of its prime ideals and all powers of them if it doesn't have these 3 graphs as induced subgraphs. Now, what are these graphs? It's 2k2, p4, and then this crazy thing of the complement of 2p3. These are the 3 graphs we want to forbid as induced subgraphs. So the point is, whenever G doesn't have these induced subgraphs, we know that all of the symbolic powers of the binomial edge ideal of G is going to have a standard monomial basis. And in particular, this is very useful for showing quality of powers, because it means that if we can show every standard monomial in the symbolic power is in the ordinary power, it implies equality of the 2. Now, next question we're going to be wondering is, what's actually in this symbolic power? We know that now it's enough to show that standard monomial is in the symbolic power and the ordinary power. How do we now tell when a standard monomial is in the symbolic power? For this, we have a new function, some alpha evaluation function, which takes in 2 things. It takes in a prime ideal in one of our associated primes and takes in any element. And what it does is it tells us the maximum number of times that element is in the prime ideal. What's the maximum power of the prime ideal such that X is an element? And in particular, this means, a simple implication is that if for a standard monomial to be in the symbolic power, if you remember by our definition of what the symbolic power was, it means that your n has to be in these powers of each of your prime ideals, every prime ideal, and that's just equivalent to saying that alpha sub p of n is always greater than or equal to t for all of your prime ideals p. Now, okay, this gives us a nice condition, but how is this helpful? And here we can use the structure specifically of our standard monomials and of our associated primes p and give a really nice condition. So what this is, whenever you have some standard monomial, or even, as we say, non-standard monomial here, which is just a product of a bunch of these terms, if you want to know how many times that whole standard monomial is in the symbolic power, it's just equal to the sum of how many times each of these things are in each of these particular primes, and then we would just take the minimum of this entire term over all p's, and that would tell us the maximum symbolic power n is in. This gives us some really nice criteria for when something's in the symbolic power. Now, this theorem is very particular to our case. This isn't true for all ideals p, certainly not true for ideals p which aren't prime, and even for a lot of ideals p which are prime, it's not true. It's specific to primes p which are of our form in which they're an associated prime for some binomial edge ideal. So what does this mean? It means that now when we understand what the associated primes are, we have a nice algorithmic way to tell exactly what is in each symbolic power, or at least which standard monomials are in them. And so the question now is, let's try and understand its associated primes. So in particular, we pick this type of graph called a threshold graph, which is a very nice pattern to its associated primes. What is a threshold graph? Well, you take some number of vertices, like n vertices, you label them from 1 to n. Then what we do is we let some of them be dominating vertices. In this graph here, 3 and 5, the two red ones, are both dominating vertices. Then I draw an edge from each dominating vertex to each other vertex with a smaller label. So 3 gets an edge from 1 to 2, and 5 gets an edge going to 1, 2, 3, and 4. Here I've drawn these edges as direct with the direction to make it easier to understand, but our graphs are going to be undirect. They're going to not have directed edges. So what are the associated primes of this? Well, again, if you remember, the associated primes get from having these types of cut sets, which means we need to cut this graph into different connected parts. Since your biggest dominating vertex connects to everything else, if you want to have an associated prime which isn't just our empty set, you have to remove vertex 5. And then, okay, now we get one, we remove vertex 5. Now, well, next 3 connects to everything else. If you want another associated prime, you have to remove 3. And so associated primes are just going to be sets of just p's of subsets of our dominating vertices. And using this, we're able to actually prove that for all of our threshold graphs and for every power, that the symbolic and ordinary powers are always going to be equal.
So we know that the equality of the symbolic and ordinary power holds for all binomial edge ideal or threshold graph. But so now we are focused on positive characteristic because we have some result there. So we are start with a definition of the symbolic race algebra. So the symbolic race algebra is the direct sum of I to the n symbolic power times t. And this direct sum is in the polynomial ring with variable t. And here we have another definition that we say that R is strong if F regular is for every non-zero element in R, there is I greater or equal than 1, such that the R linear map from R to the 1 over P to the E defined like this splits over R. So don't worry about this definition because we're going to prove this property with a lemma. So why we care about it? So we know that there is a connection between the commutative algebra and algebraic geometry given by some kind of ideals. We can associate it variety, and geometry, these varieties has singularities. So this property is a nice type of these singularities, And here we can see two examples of ring with this property. The first one is the determinant ring, and the second one is the Veronese ring. Now, we will use this lemma from Ramírez-Moreno to prove that the symbolic Riesz algebra is strongly irregular. So let G be an homogeneous radical ideal. Let P1 up to PL, the primes in the decomposition. Let Hi the height of each prime, and let M be a relevant idea. And let F an element of S shows that F is equal to C times G, where S and G are in S and C is not zero. So suppose the following holds. First one, G is in this intersection. The second one, F to the P minus 1 is not in the maximal to the Frobenius power. The third one is this localization is strongly F-regular. And the last one is that the symbolic Riesz algebra is Noetherian. So then the symbolic Riesz algebra is strongly F-regular. So we have a theorem, let G be a threshold graph, then the symbolic Riesz algebra of the binomial ideal of threshold graph is strongly F-regular. So now Megan is going to explain the idea of the proof with an example.
So take a threshold graph with dominant points 3, 4, and 8. We're going to take G, the element given by the Hamiltonian path in red, and we're going to show that F, the product of G and C, it satisfies the lemma above. So, okay, in this case, we have that the prime decomposition is this one. And since G is obtained by a Hamiltonian path in the complete graph, recall that a Hamiltonian path is a path that visits every vertex once. So G is in the 7th power of the complete graph in the vertex, and that is a subset of when it's traced into the 6th. You have these contentions, and with that you can show that F is indeed in the intersection. And noticing that the leading monomial of F is square free, and since M is monomial, then F rising to the P minus 1 is not in the maximal, in the Frobenius power of the maximal ideal.
Now we are going to prove that this localization is strongly F-regular. So we have that the binomial ideal localized in this element is equal to the intersection to localize each prime in this element. So notice that the element X8 appear in all the primes in this decomposition except in the binomial ideal of the complete graph. So in the localization, X8 must be a unit, so we can remove all these primes. So we have this equality that the binomial ideal localized in X8 is equal to the binomial ideal of the complete graph localized in X8. And this happened because X8 is the last dominant point. And we know that this ideal is a strongly irregular but hosted and unique. Then we have that the binomial ideal localized in X8 is strongly regular. Thus, this localization is also strongly regular. Now we are going to prove that the symbolic Riesz algebra is Noetherian. This is because we have this equality from this binomial ideal, and we have that the Riesz algebra is equal to the symbolic Riesz algebra, and we know that the Riesz algebra is Noetherian. So this symbolic Riesz algebra is also Noetherian. Thus, by Ramírez-Moreno lemma, the symbolic Riesz algebra is strongly irregular. Thank you.
Hi, questions from the speakers? Charlie.
Yeah, I have a question. There was a slide where it showed a Hamiltonian path in the threshold graph.
Yes.
Wait, I think I'm confused. Why is like 1 and 2 connected? And why is 4, 5, and 6?
Oh, it's a Hamiltonian path on the complete graph, not on the threshold graph.
Oh.
Yes.
okay, I see. And then I also have a question, earlier in the slides, there was, you said that the cut sets of the threshold graph correspond to like subsets of the dominant vertices.
Yeah.
But you had, for that example, you had like dominant vertices like 5 and 3. And so cut set was like 5 and 3, 5, but there wasn't a cut set.
Yeah,
Right?
I mean, I kind of skipped over the nuance here, but the point is just, if you just remove vertex 3, that wouldn't get you anything, because 5 still connects to everything else. So each of your cut sets is going to be a sequence of like the n biggest dominant vertices, for example.
Okay.
So we just get like no dominant vertex, the biggest one, the next two.
Yeah, whenever a dominant is in a cut set, all the greater graphs should be in the.
Can you explain, like, vaguely the intuition of why those 3 graphs define having the Plucker freeness, like what is it, 2K2P?
Yeah. Okay. So if I go back, or let's see. So the main point here is there's not really a general intuition for like 1 and 4 are necessarily equivalent. It's more you go through these other steps here. I mean, the reason why 1 and for example, like 1 and 3 are kind of equivalent are if you have some vertex in your complete part, which is like let's say one of your complete parts doesn't have the vertex 1, you can like pair it off with some other one, and then there's some Plucker relations that kind of get you outside of that piece. That's like why 1 and 3 are equivalent. As for like 3 and 4, you'll notice that like these 2 graphs, for example, if I go to the next slide, you can see these 2. You can divide it up into 2 different parts, which are going to have 2 different complete parts. So there's going to be some cut set that isolates these 2 vertices as one complete part, and these 2 as another one. So you're not going to be able to label them both from 1 up to m. Similar to P4, you can isolate these 2 as one connected part, these 2 as something else. I mean, there'll be other vertices in those connected parts, but it'll be destroyed from the other ones. And so it gets you a similar property. Same thing happens for 2. Problem 2.
I mean, the complement of 2B3 is like the odd one out.
Yeah, I mean, here the case is, this is when you're gonna have, let's see, I think it's like these 2 vertices. You can, like, if you remove like these 2 or something, or you remove like these 3, some combination, you get like 2 different you're gonna get 2 different connected parts which are disjoint, and so they can't both be labeled from 1 up to some number.
Sure, okay.
Yeah.
More questions? Okay, let's thank the speakers again.